be able to solve a compound linear inequality and then graph the solution on a number line. All right, a compound inequality means there's going to be more than one inequality sign in the problem. It gets a bit complicated. So you're really going to have to focus on when it works one way and when it works the other way, okay? So, inequalities containing the word and. When considered together, two inequalities such as 5 is greater than or equal to 52 and 5h is greater than or equal to 52 and h is less than or equal to 72 form a compound inequality. A compound inequality containing and is only true if both inequalities are true. That's just a math fact. That always works that way. Whenever you say something in math with the word and, the only way that the statement can be true is if both parts of the statement are true. If I say today is Monday and I have $10 million in the bank, that's a false statement. Part of it's true, part of it's false, that's a false statement. Okay, that's the way it works in math. Okay, now, when we have this, let's go with the one they gave us. H is greater than or equal to 52, and H is less than or equal to 72. This first one, H is greater than or equal to 52, if I flip that around, like so that both of my inequalities are less thans, whenever you have an and, it's convenient for both of your inequalities to be written as less than. Because now I can write this in a little bit shorter version. I can do 52 is less than or equal to h. And then instead of writing and h again, just say, I say and h is less than or equal to 72. And it's worth writing it this way. That's truly now called a compound inequality. Okay? And it's worth writing that way because if I make a number line, I know where h is. All right? H can be equal to 52. It can be equal to 72. And then otherwise, where is h? In between these. Just like it is when I wrote it out in symbols. H is between them. Okay? Does that make sense? Okay. Now, let's go back to what this is. All right, its graph is where the two inequalities overlap, because again with this one, if I graphed h is greater than 52, greater than or equal to, I'd color that in, and I'd do that, right? And if I graphed h is less than or equal to 72, I'd color that in, I'd go this way. Where do the two graphs overlap? Right here where I said they did. With an and, it's where the two graphs overlap. Because where the two graphs overlap are the solutions of both inequalities. It's got to be both. Okay? Got to be both. Now, where they overlap is called the intersection. You need to know that so that we don't have to keep saying where they overlap. We'll say the intersection. The solution must be a solution of both inequalities. Otherwise, the compound inequality has no solution. Well, let's look at the one they've done there. They graphed x is greater than or equal to 3. They graphed x is less than 7. Where do the two graphs overlap? Right there. So, what are the solutions to this compound inequality? Between 3 and 7, including 3 because that was colored in, not including 7 because the 7 was not colored in. Make sense? That last thing I circled, that's the solution of that. Because it describes where the numbers are that make it true. Pick one out that's in here. Does 4 make that true? Is 3 less than or equal to 4? Yep. Is 4 less than 7? Yep. 6. Does 6 make it true? Is 3 less than 6? Yep. Is 6 less than 7? Yep. The one we did here, 60. Is 60 greater than or equal to 52? Yep. Is 60 less than or equal to 72? Yep. So where the graphs overlap of the two parts, of the two inequalities, that's where the solutions are. See what I said about this starting to get complicated? All right. Let's do this one. We're going to solve this, then we're going to graph the solution set. Now, don't write down what I'm going to write down first. I can break this in two. I can do that. And then I solve this one, I solve this one, and then I put them back together for the solution. Don't do it that way. That's the hard way. Okay? Instead, what I'm going to do is this. So now you can write down what I'm doing. I'm just going to write the problem down first. And then I'm going to pretend for a moment that that part's not there. If I wanted to solve that, wouldn't I simply add 3 to both sides? Okay, so negative 2 plus 3 is 1, is less than or equal to x minus 3 plus 3 leaves me with just x. Now I'm going to pretend that part's not there. What would I do to solve that? I'd add 3 to both sides. I've already added it to the x minus 3. Add it to the 4. I'm done. That's the solution. Okay? Now, I'm not going to continue to cover up things with a little box here. All right? Instead, I'm going to say, if it was a regular equation or a regular inequality, we would add 3 to both sides. Well, there's 3 sides now. Add 3 to all 3 sides. Now, these aren't always one-step problems. This one was because here in the middle, it's just an x. Isn't that always when we're done, when we're solving? Well, so we're done. Okay? Now, what does this mean, though? Well, it means that if I take a number line and I start at 1 and I end at 7, see how it's 1 is less than or equal to x? Closed circle. X is less than 7, open circle. See how x is between them when I write it in symbols? X is between them when I graph it. So any of the numbers that graph crosses over, like 2, 3, 4, 5, 6, 6.9, 1.1, 1, all of those are solutions. Okay, so how many solutions are there? There's an infinite number of solutions because there's an infinite number of numbers that this goes over. Okay, not just the whole numbers, but the decimals and the fractions and all that stuff too. All of those are solutions. We okay with that? Okay. All right, next example. This time, they write it as 2 separate things. I would like to, if possible with an and, turn this into one inequality, one compound inequality. So if I take this one, when I write it as one compound inequality, both of my signs are going to be less than. If I take this one, I need to flip it around to turn it into a less than. So I'll make that negative 11 is less than or equal to y minus 3, and y minus 3 is less than or equal to negative 8. See how I turned that into one compound inequality? You can always do that with an and. Always. You can usually do that with an and. Okay? Once I've got that, what do I need to do to all 3 sides of this inequality? Add 3. Negative 11 plus 3 is negative 8, is less than or equal to y minus 3 plus 3 is y is less than or equal to negative 8 plus 3 is negative 5. So any number between negative 8 and negative 5, including negative 8 and negative 5, will make a true statement. Graph it, negative 8, negative 5, closed circle, y is in between them. Do that next one by yourself. Yeah, all we got to do to make it more steps is instead of r, call it 2r. And then after you subtract 7 from all, then you have to divide by 2. Your answer look like my answer? Good. Any questions? Now, if that were the only type of compound inequality, we'd work 15 of those. We'd get really good at them. It's not the only type of compound inequality. And here's where, really hang on here so you don't get confused, okay? That's how you work them with an and between the two inequalities, okay? Or written as one compound inequality. But we can have or. Now, in math, or means that if anything I state is true, the statement is true. So if we go back to today is Monday and I have $10 million in the bank, that's false because I said and. But if I say today is Monday or I have $10 million in the bank, that's a true statement because part of it is true. So with an or, another type of compound inequality contains the word or. A compound inequality containing or is true if at least one of the inequalities is true. As long as one of them is true, the other one doesn't have to be true, and it's still considered a true statement. I know, right? Doesn't seem fair, but that's the way it works. Okay? And let's face it, you've probably done that to your parents at some point, right? You used or to try to kind of get away with it. Hey, what'd you do all afternoon? Or what are you going to do tonight? Well, we're thinking about going to a movie or maybe just go somewhere else and hang out. Right? The or's always the bad part, right? But you, in your mind, you're saying, I told the truth. We're going to do one or the other. Okay? So don't do that. That's not nice. You can do it with math, but not real life. Its graph is the union of the graphs of two inequalities. A union, instead of an intersection where the solutions the two graphs had in common, where they overlapped, a union, as long as the number's on either of the two graphs, it's part of the solution. So its solution is a solution of either inequality, not necessarily both. It can be both, but either. So look, here's the graph of x is greater than 2. Here's the graph of x is less than or equal to 1. Here's the graph of the solution of x is greater than 2 or x is less than or equal to negative 1. And there is no way to write that without the word or. You always have the word or in there. You cannot eliminate it. Okay? That's the only way to write that solution. All right? Any questions? Let's see how it works out. Solve negative 2m plus 7 is less than or equal to 13, or 5m plus 12 is greater than 37, then graph the solution set. All right, here we go. Let's solve the first one. Negative 2m plus 7 is less than or equal to 13. First step, I do what to both sides? Subtract 7. I get negative 2m is less than or equal to 13 minus 7, 6. Now I do what to both sides? Divide by negative 2. And when I divide by negative, I do what to that less than or equal to? Change it to a greater than or equal to. And then what's 6 divided by negative 2? All right, there's 1/2 of our solution. Or 5m plus 12 is greater than 37. Subtract 12 from both sides. 37 minus 12 is? Divide both sides by 5. Okay? Now, so far so good? Any troubles? All right. Let's see, I need negative 3 on here. I need 5 on here. M is greater than or equal to negative 3. Closed circle, greater than, to the right of negative 3. M is greater than 5. Open circle, greater than, to the right of 5. Now, that's a weird looking graph, and that's not going to fly. Remember that our solution, any number that's a solution of either one of them, isn't everything from negative 3 to the right the solution of at least one of those? Isn't everything from here to the right a solution of one of those or both of those? So everything that I just colored in red is a solution because it's a solution of one or the other or both. I forgot to mention that possibility, or both. Okay? One or the other or both. So the actual final answer to this graph is that. I needed to do the other to figure that out, but that is the actual graph of the solution. Questions? All right, was that the only one on this slide? Yep. All right. Let's take a look at 3A here. A plus 1 is less than 4. Subtract 1 from both sides. A is less than 3. Or A minus 1 is greater than 3. A minus 1 is greater than or equal to 3. Add 1 to both sides. A is greater than or equal to 4. And it's got an or between them. In fact, I really should write out the word or between them. Okay? That's my answer in symbols. That's it. I'm done with the solving of it. Now, graph the solution. Well, I'll put 3 on here, and I'll put 4 on here. A is less than 3. Open circle. Numbers less than 3 are to the left of 3. A is greater than or equal to 4. Closed circle. The numbers greater than 4 are to the right of 4. They don't overlap, so I don't need to simplify the graphing. That's it. That's the solution. That's the graph of the solution. So that's the solution written out. That's the graph of the solution. You with me? Let me go back here. And it bothers me that I forgot to write the word or. So that was the solution there. That was the graph of the solution. Do 3B and see what you come up with. Now, you don't have to, to draw two graphs like I did. I just wanted you to be able to see my thought process here. I thought I was going to be done there, but I wasn't, was I? There's a better graph than that. That is a better graph. So you don't have to draw it again. You can just do a little erasing and fancy it up. Or draw it again. It may be easier to draw it again than it is to erase. We okay with that? Everybody get what I got? Now, I need to show you something here. Let's take that same problem and let's change that or to an and. And let's say that I don't think of writing it as a compound inequality. That doesn't enter my mind. So I do this, that's solved, then I do and, then I write this, then I do 4x is less than 8, x is less than, wait a minute, yeah, 2. And so with an and, when I graph this, I'd put a 2 on here, I'd put a 9 on here. X is less than 2 is going to be that still, right? X is less than or equal to 9 is going to be that again, right? Now, look, that graph and that graph are the same graph, aren't they? Okay? But remember what and means? To be a solution of an and, it has to be a solution of each inequality. So if I get a final graph for this, where are the numbers that are on both graphs? It's those, isn't it? Those are the ones on both graphs. So you got to be careful. Okay? Now, how would this have worked out if I had tried to write this as a single compound inequality? Again, I'm changing that to and. Okay? So I would do 9 is less than or equal to x, and 2 plus 4x is less than 10. And you see where I wouldn't be able to combine those into one compound inequality? Because it's not the same thing there. Notice if we flip back, it was the same thing in both cases. It was a y minus 3 and a y minus 3. It was just an r plus 7. It was an x minus 3. But on this one, I can't do it that way. Even if I want to, I can't, because it's not the same thing on both of them. You know, see what I'm saying? All right. I'm going to give you a worksheet and let you work.